here is roughly control and stability analysis of converter-dominated power systems. And I will first, do a bit of a tutorial-style overview of kind of standard existing results, and then, basically dive a bit more into my research, and then at the very end, kind of give an outlook how all of this in the future hopefully relates to big data and data-driven control and so on and so forth. So to set the scene, here's basically what we are all aiming for or hoping for, that we can replace emission-heavy fossil fuel-based generation with renewables that are hopefully clean and sustainable. And if you were to ask people on the street, like, what's the major problem here, then of course, this is dispatchable, so this can follow the load, whereas the renewables here, basically, they generate power whenever the wind blows. And this obviously has been the subject of a lot of, data analytics approaches to come up with prediction models to handle the stochasticity and the generation here. So this is not what this talk is going to be about. Instead, there's also a change under the hood in how this generation technology is interfaced to the grid. And we see here that the conventional generation is typically interfaced through synchronous machines that have a lot of kinetic energy stored in their rotating masses. So basically the kinetic energy stored in the rotating mass here of the machine, that's the only instantaneously available energy buffer on today's grid. So this is energy storage that you basically leverage on the scale of milliseconds to seconds. And also, these synchronous generators, they inherently self-synchronize, that's the name of the synchronous generator where this is coming from. And they've been basically well-established technology for a long time and fairly well understood. And now we're interfacing the renewables and batteries and so on through power electronics. And they, first of all, don't feature a lot of internal energy storage. They do not have the same inertia response as the machines. So this is typically seen as a problem in the community. I will put a bit of an asterisk on that in a moment once we get deeper into the results, showing that that's actually maybe not the biggest problem here of this transition of the underlying technology. And so, as I was already mentioning before, one of the key points here is that for synchronous generators, we know that, on very fast timescales, their control is very reliable, their fault write-through properties are very reliable. And at least for the grid following type renewables connected to the grid today, that's not really the case. So the only upshot then here on this kind of side of the power converters and renewables is that they have very fast actuation capabilities, and we can very flexibly control them. So whereas over here for the machine, overall the dynamics are basically governed by the slow physics of the machine, and they're highly nonlinear, and then there are a few control loops around this. But mostly what happens on very fast timescales with the machines is basically just governed by the machine physics. And this is where there's a lot of leverage on improving actually the situation and the system performance by fully leveraging the fast actuation capabilities of the power converters. So just a quick overview over this talk here. First, I want to talk a bit about the role of inertia. How does it impact systems if you transition to low inertia or no inertia systems? And what role does the converter interface generation really play? So the first point here will just be a bit of a recap of why do we even need rotational inertia and how much may we need in a future system. And then I will talk a bit about what the impact of converter interface generation on the frequency dynamics at the system level really looks like. And what I underlined here is the generation part in converter interface generation, because we will really see a lot of this comes down to how quickly your power source or your generation unit can respond, and basically making sure that you can get that passed on to the system level. Then I want to talk a bit about grid forming and grid following control. So these are basically two different principles to control power converters that interconnect renewables or storage systems to a grid. And we've recently developed a universal control paradigm where these two things kind of are subsumed in one single control that doesn't have any mode switching between different control modes. And for this, we can give relatively strong stability results. But as you will see, they depend on the properties of the generation, of the power conversion, and also of the network. And this is information that you may not have available. And then that sets the scene for, at the very end, I have a few slides as to how can data enter into this picture? Can we leverage data to actually understand some of these things and to verify some of these stability conditions and to validate, that the converter interface generation is actually doing what it's supposed to be doing based on measured data. Okay, so jumping into the first topic here. So what's the role of inertia really? Because people have gotten very hung up on these low inertia systems. So over here you see a second order differential equation model of a single synchronous machine that is sketched over here. So we have the rotating mass, and then there's basically torque or power balance on the rotating mass. This is what you see here. We have a rotational frequency, omega k of the rotor. And then one important thing that is often overlooked in the analysis, we also have dynamics of the turbine here. So you can imagine if there's a increased demand or increased load in the network here, you first supply that from the rotating mass, so you're drawing more power out of the machine. The rotor will slow down. This gets picked up by the governor system that senses that the frequency dropped or the rotation speed of the machine, and then activates the turbine. So if it's a steam turbine, lets in more steam to generate more power. And obviously this process, has time constants associated with it. And this is not instantaneous, right? So you open a valve, you get more steam into the turbine, pressure builds up, the turbine starts, generating more power. So this is basically captured by this equation here. And now from a kind of system level point of view today, the key properties of these machines are that the power flowing between the machines is proportional to the angle difference and the line parameters. So this gives you a notion of self-synchronization of different machines. So at the end of the day, every machine, has its own rotor frequency, but then very quickly they self-synchronize through the network. And this, for all the higher level controls, they then think of, a system frequency, even though that doesn't really exist. So the machines basically self-synchronize through the power flows of the system because those are dependent on angle differences, and then the power gets mapped back to the frequency. Angle is integral of the frequency, so that way the machines self-synchronize. Then the inertia basically acts as a buffer for the slow turbine governor response. So while the turbine is ramping up or down, the rotating mass here acts as a kinetic energy buffer that is just basically smoothing out any fluctuations in the system. And then on top of this, as I mentioned, we have the primary frequency control. So the governor system here, we have voltage regulation, we have the power system stabilizer. So this is just to give you an idea that the machines are providing many different services and have many different underlying properties. And by replacing machines now with, power electronics and renewables, we're not only losing the inertia, but we're basically losing all of these functions here if we don't do it correctly. And nonetheless, in the literature, you will find a lot of focus on this low inertia aspect, so on losing basically this energy buffer. So here's just a crude mix of different, concept papers, documents put out there by system operators. A European project that was running up until maybe 3 years ago. And at the same time, this all seems a bit exaggerated in the sense that you can find a lot of works on, how to emulate the machine inertia using power converters and storage. And what most of these works have established, and I will get to that in a moment, that you can actually replace the synchronous machine and its slow turbine response with something that's called a grid forming power converter that, has similar self-synchronizing properties to the machines and a fast frequency response. So basically, if you have a source that responds very quickly, you can have the equivalent of a very fast turbine governor system, and then you don't need a lot of inertia. Or if you want to, you can use these things to emulate an inertia response, but that may end up quite expensive as you will have to oversize the converter and put in a lot of storage to actually supply these things. So that's the theme. And diving into this a bit more, let's see what actually happens if you were to replace a synchronous machine by something that looks like a synchronous machine but has very little inertia but a very fast turbine. So to clarify how these two parameters influence the system level frequency dynamics, let me use the standard center of inertia frequency model. So this is a model where basically you use a weighted sum of the generator frequencies to model the system frequency. And as we discussed, the inertia acts as a buffer for the slow turbine. So you can see here, if you put a load step into the system, here's the frequency response of these kind of center of inertia frequency, system frequency dynamics. If you decrease the rotational inertia m, you see that the frequency dips faster. So you have higher rate of change of frequency, and it dips to a lower value. So you have a lower frequency nadir. And this is obviously problematic. And this has been basically a proxy for what happens if I take a power system as it is, I retire large-scale power stations with turbine governor systems and inertia, replace them by power converters that only have a constant power in feed, so they do like maximum power point tracking, and I would crank up the governor gains of the remaining machines to kind of keep the same frequency regulation. So this is where this curve here is coming from. But then now suppose we can control converters to actually contribute to frequency stabilization and all of these things, then they will basically look like, and I will show examples for this in a moment, like very fast, like machines with a very fast turbine governor system. So to clarify the impact of the turbine time constant, we can rescale time of these dynamics here. So basically this time here becomes 1, and this is equivalent to stretching the time axis here. And that doesn't really change the frequency nadir, it will change the Rokov, but I'll get to that in a moment. So let me change time and normalize time basically. Then the system frequency dynamics will look like this. And you now see here the ratio of the kinetic energy and the turbine response showing up. And this actually governs how far your frequency drops. So ultimately, the frequency nadir actually scales with the ratio of the inertia to the turbine time constant. So if you improve that, the frequency will not drop so far. And if you change the turbine time, that basically just determines when you reach the frequency nadir. So with a very fast turbine and very small inertia, you get to the frequency nadir earlier versus with a machine with a slow turbine. It's basically just going to happen at a later point in time. And so the fact that the response is kind of determined by this ratio here is good news, because the power source that is actually generating power or providing power, if it's a wind turbine or a battery or PV, that's orders of magnitudes faster than what a steam turbine or a hydro turbine can do. So if it's only this ratio here that matters, that immediately buys you that you don't need to emulate a lot of inertia to basically maintain the system frequency within the same bounds. Caveat that I should mention is that the rate of change of frequency, so how quickly the frequency drops here, this is still approximately linear in the inertia that you have on the system. And that's going to be a problem because this is oftentimes used for protection. So loss of mains protection looks at the rate of change of frequency. The protection of existing machines looks at the rate of change of frequency at the machine bus. On the other hand, for converter interface generation, the rate of change of frequency is not really such a big problem because the converter itself has no rotating parts, it's all just electronic. So the frequency could even jump and it wouldn't be problematic if you have a proper control that allows to leverage these things. So key message here is that the loss of inertia is a bit exaggerated in the sense that if you were to replace synchronous generators with something that has roughly the same self-synchronization properties and so on, and primary frequency control, but can do that a lot faster than a steam turbine, then you need a lot less inertia in the system because it's just a buffer. And to highlight this, here are a few tests that we did. So this is from an EMT simulation with relatively high order machine models and converter models. And this was tuned in such a way that the grid forming power converters, those are connected here, they basically did not provide any virtual inertia. And then we compared the standard IEEE 9-bus system that had 3 machines, so one at bus 1, 2, and 3, to one where 2 of those have been replaced with grid forming converters. And then you see we basically randomized different load steps and things in the system and compared this for different controls on these converters here. I will get into what these different controls are in a moment. That's not too important right now. But the key message is that this is normalized so that basically 100% here means the all synchronous machine case. And then the first plot here shows you what happened at these different samples in terms of the rate of change of frequency. And here, what happened in terms of the frequency nadir. And you see that if you go to a system that has two machines replaced with the power converters, using, again, different controls, so there's yellow, red, purple, and blue here, just different controls, you see actually a large improvement both in the rate of change of frequency and in the frequency nadir. And this is just down to the fact that these devices can provide a primary frequency control response basically without any delay, or with very small delay, like in the range of milliseconds. That's for the machine, you have this first order behavior of the turbine governor system in between. So we can also, this is a very detailed simulation. We can also look at these things based on a simplified model. So I don't want to bore you too much with the math here, but this is basically a model of a two-bus system with a power converter here that's using something that's called group control. And here we have kind of the standard machine model with angle dynamics, frequency dynamics, and turbine dynamics. This parameter mu here is the rating of the grid forming converters relative to the machine. And can now go through a few model reduction steps. So we can first recognize that, we can get rid of these two angles here by only looking at the angle difference in the system. Gives us something like this. And you see here the angle difference being driven by the response of the grid forming converter and the machine frequency. So modifying this a bit more, you can see that this inertia constant here and time constant of the turbine of the machine is relatively large as to compared to the speed of the angle dynamics here. I will get to that question in a second. And so you can basically treat these angle dynamics here as very fast, eliminate them, plug them back into here. And what you will see is that basically now the primary frequency control response provided by this, by the power converter looks like pure damping on the machine and doesn't go through this turbine governor system here. And if you actually use that very simple model that I just showed you here to predict, how the rate of change of frequency and the frequency nadir will change as you transition from the 3 synchronous machine IEEE 9 system that I showed you to one that has 2 power converters, you get that the rate of change of frequency will drop to around 40% of what it was before, the frequency nadir roughly the same. And if you go back here, you would see this is approximately where these controls here ended up, the faster ones. So from a qualitative point of view, you can explain this fact that the fast frequency response of these converters can replace the slow synchronous machine turbine governor system, without actually emulating any inertia. Okay, so there was a question in the chat of where's the source of nonlinearity in the system. Could you maybe elaborate which nonlinearity you're referring to?
Oh, sorry. Yeah, because usually, I think the power system synchronization dynamics system is always nonlinear, but
Yes.
your system looks linear. So
I mean, this is the linearized.
Oh, it's a linearized.
Yeah. So here, let me go back. So, here you would have the sign of the angle differences.
Okay.
And then, for these simplified analysis that I show here, this is linearized at 0 angle difference, and then it disappears.
Okay. Yeah. So does this set up? Yeah. Does this set of 2 equations include any renewable sources?
Here, not yet. No. This is
not yet. Okay.
What these equations are basically outlining is just imagine I could give you a machine that has very little inertia, but a very fast turbine. How would that change the system?
Oh, okay. Okay.
What we will get to in a moment is that, if you have something like a grid forming power converter, and I will also get to, explaining what that actually means, it will look like this.
Okay.
But that still doesn't include any renewable sources. This still, assumes that it's backed by a battery, and then there's one more step to get the power source into the picture. Okay.
Yeah. Okay. Thanks. Yeah.
Yeah. Thanks. Okay, so wrapping up here, you can basically see that if somehow we can manage to control these converters like a machine with a very fast turbine governance system, then we're in business and we don't really need all of this inertia. I should also emphasize here that this analysis that I showed you and the EMT simulation results from the IEEE 9 bus system, that's valid for systems that are very strongly coupled, so that, are very tightly connected and have short lines. Then you can replace basically the frequency dynamics of the system with the center of inertia frequency model that I was using that looks like a single machine. As I was mentioning, all of these machines actually have different frequencies at their buses. And, if the coupling is relatively weak, and one example for this is the Southeast Australian power system that you see here, where these areas here correspond to these different geographical areas, then that's no longer the case. And then it becomes a bit tedious to understand, like, what's the impact of inertia on the system. So a few years back, we looked at this and we basically optimized the placement of power converters that can emulate inertia. So basically we retired a few machines and then we asked, like, okay, what would be the best place to put devices emulating the machine inertia? And we used an optimization-based approach that's following using the H2 norm. Sorry, somehow okay, here it is. So we came up with a relatively efficient optimization algorithm that turns this into a structured control design problem and then allows us to minimize a metric that basically measures how disturbances are amplified throughout the system. And here's the result. The key point is maybe not what this looks like. So you see here the frequency at different buses. And the original system, after retiring a few machines, are these blue curves here. So this is the response to a load step. You see it's fairly ill-behaved and oscillatory. And then if you optimally place different inertia devices in the system where you get the yellow response or orange response, that's relatively well-behaved. But the problem is this, it's the total inertia in the system is not really a good metric anymore. So if I take the same amount of inertia devices that I've used for this optimal allocation here and put it in a suboptimal location, then I get this blue response here. And you see this is almost as bad as the original low inertia system. So one of the caveats that I need to mention here is that everything that I showed you before, it's for very strongly coupled systems. And then it's really mostly, the total inertia and the total turbine delay of the machines that governs what the frequency response looks like. But if you have a system like this, very large, and then, very weak coupling from this part to this part here, then it really also depends on where you're putting the inertia. And I will get back to this at the very end, hopefully. The big question here is then, to optimize this, you need a perfect model of the system. You need to know, what the generators are doing here, what the coupling looks like. And of course, in such a large scale system, you typically don't know this. So this is one of the questions where data and, collecting a lot of data from, from synchrophasor measurements, smart meters and whatnot throughout these systems may actually help to better understand where are weak spots in that system that need to be reinforced versus, having a perfect model of all of this and then solving an optimization problem to find the optimal allocation. Okay, so now I was talking beforehand about, this mythical grid forming control. So let's talk a bit about what this is and how renewables factor into this mix. So if you look at actual contingencies in power systems, they're very rarely related to this loss of inertia. So here's basically an overview over things that happened in actual power systems that have a large share of converter interface generation. And we'll see they are mostly related to control. So there was a massive blackout in Australia in 2016, and this was related to fault ride-through of wind turbines. There was a near miss in the Western interconnection in the US. That was already 50% of the design contingency of the Western interconnection. And this was related to an estimation algorithm in the grid following control screwing up and basically taking 1.2 gigawatts of PV offline. And there was another kind of incident of a system split in Australia in 2018. And this was actually this very fast response that I was alluding to as something positive before, and the very fast response of a battery energy storage system was not compatible with the legacy protection system and actually tripped off an interconnector. So these are all the problems that you will observe in actual systems, is that some controls lack basic robustness and resilience properties that synchronous generators have, and this is unrelated to inertia. Then standard timescale separation assumptions, where you assume that, all the machine dynamics are slow, so I can neglect the network dynamics when analyzing those, doesn't work anymore. And then the biggest problem is actually interoperability between all of these converter interface devices that are integrated into the grid with legacy devices and protection. There's basically very few guarantees on these things. So how does it work today, and why is there a problem? So here's how renewables would be integrated into the grid today. So you have your AC grid, and you basically just treat it as a stiff AC voltage source with a near constant frequency, near constant magnitude, and there is some sinusoidal waveform here. So the idea is that the AC power system is almost an infinite bus. And then the model for the converter from the system point of view is actually that, I have this AC current source feeding into this infinite bus. And the way I'm doing this is I have something that's called a Festlock loop that's measuring the phase angle, or is estimating the phase angle of this voltage waveform here, turns that into something that the converter can use for its control. And then where the converter basically controls the power injection on its AC side to keep its DC side stable at the maximum power point, for instance.
Hey, Dominic,
Yep.
There's another question
Yep.
from Professor Amar, and he's from Arizona State.
Yep.
Yeah, he wants to know, can you please explain what the difference is between fast frequency response and virtual inertia? That's question number one. Question number two, does that virtual inertia limit the ROCOF while fast frequency response limit the NADIR?
Yes, that's roughly correct. You can think of, so the term virtual inertia has been abused quite a bit in the literature to describe a lot of different things. But if you really go back to the inertia response of the machine, then virtual inertia would be a proportional a power injection by the device that is proportional to the rate of change of frequency. And that would then, decrease the rate of change of frequency, but it would not necessarily do a lot to the frequency nadir, depending on how the system is configured. Whereas the fast frequency response would basically be a primary frequency control response, so power injection proportional to frequency deviation, just doing that with a very small time constant versus the very long time constant of a steam turbine.
Okay. Yeah, there's a question from Hamad from Kuwait. Is it a challenge, hardware of the control, actuation, and implementation, or more towards software modeling and algorithms? So yeah, this is a student question.
I would say it's both, in the sense that at the moment, I think the problems are less on the hardware side. So there's one severe problem on the hardware side, and that is current limiting and fault right through. So if you look at that space, you cannot emulate the fault response of a synchronous machine with a power converter without oversizing it dramatically. So this is a hardware limitation, and this comes from the fact that the semiconductor switches in the power converter have typically overcurrent capabilities in the range of maybe 20–40%, whereas a machine can go 3 times over its rated current for 100 milliseconds or so. So that's a bit of a hardware issue, but generally, the hardware is very mature, and most of the problems are on the control implementation and analysis side, I would say. So the control implementation problem here, and this is also something I was hoping to get to a bit later, is that obviously as a system operator, you cannot force a vendor, implement a certain control in its converter. You can give them standards and guidelines, but whatever they program in there, that's their secret sauce and their what they're doing. So that's from the implementation side, a bit of an issue that people can basically put in there what they want, and now the question is, what type of standards can you put around it to narrow down what they're doing so that all of this is working together. And this is kind of a non-issue right now because, as I mentioned before, on those fast timescales, the response of a synchronous machine is mostly governed by its physics. I mean, there is no software there. There is not a software switch that someone can flip and change the response completely, but with a power converter, I can do that. So from that point of view, it's maybe not the implementation per se that's a problem, but how do you validate that the implementation is correct becomes very challenging. And then there's certainly kind of an analysis and stability certification problem, because the way you're ensuring interoperability and stability of these things right now is that you basically just run massive simulations, right? And you run a ton of different case studies. And that's fine if you have a few hundred of these synchronous generators and you can come up with reduced in a system like the European, continental European system. And you can come up with a good reduced order model that has maybe 20 generators in there. I mean, then it's feasible. But now imagine that we have a future where you have like millions of rooftop PV devices, utility scale wind farms and PV farms, and you can just not run so many simulations anymore. So you will need some sort of stability certificate, that you can put onto that system and be sure that everything works together without actually having to simulate, these like doing time domain simulations of systems that have millions of devices. So I think that's ultimately the biggest challenge here.
All right. Thank you so much.
Sure. And yeah, I mean, this boils down to what we're seeing here. So that's the standard control loop. And as I was mentioning, this is also something you will find in an HVDC converter, for instance. So it's basically all predicated under the assumption that the grid is stable as is, and I can log on to the grid and follow that along. And then, I basically control the power injection on the AC side here to meet some control objective on the DC side. That may be stabilizing the voltage of a DC cable. It may be extracting maximum power from your PV panel. But the assumption is, I can push whatever power I want from the DC to the AC side. The system will take it, and the system frequency will not really change. And that's, of course, not how this is going to look like in a future system. So this is valid right now if you have a lot of large-scale power stations and very few converters. But now imagine that, these converters here dominate the system, then no one is forming that stable AC voltage waveform here to log on anymore, and then we have a problem. So that's the story with the grid following control. In this contingency, with the loss of the 1.2 gigawatt PV generation, the Western interconnection that I showed you before was basically down to this phase loop algorithm here failing because of there were lines tripping. The waveform over here was no longer perfectly sinusoidal, and then this phase loop here, this PLL algorithm failed, and the PV just disconnected. So yeah, that's what I just said. So let me skip over this. So this is just more illustrations of this point that, this phase loop and this assumption that the grid is stable, those are quite problematic. Now there's an opposite paradigm here that I was already alluding to before, and this is the grid forming control. And this is basically saying, let me ignore what's behind the power converter. So now the power converter is measuring the power injection into the grid, and it's imposing a stable voltage waveform here. So meaning stable frequency and voltage, they may change, they're not constant. And it's just assuming that the power source behind the converter can keep up and provide any power that is needed to do this. So the assumption here is basically, standard control in the literature would be droop control, for instance. So the assumption here is then that, the DC terminal of the converter is an infinite bus from which I can draw whatever power I want, and the DC voltage doesn't change. The converter model is basically that you model it from the system point of view as an AC voltage source that's feeding power into the network, and there are no current or power limits. And then the objective would be, let's stabilize the AC network at the desired operating point. So basically, a more accurate description of what's going on here is that this is AC grid forming, but it's DC grid following, because it assumes, that the DC terminal of the converter is stabilized by some other device. And typically that will not mean then we put a battery here, right? Because if I have renewables here, I cannot really guarantee that this voltage is stable at all times. And that's resulting in quite a few challenges. Before I go on, let me maybe just briefly point out where does that control actually factor in. So here is kind of an expanded view of the power converter. So you see a typical 2-level voltage source converter setup where you have a DC voltage, some DC source, and then the DC voltage is modulated in into an AC voltage. There's an RLC filter here to remove switching harmonics. And then you have underlying current and voltage control loops. For the purpose of this talk here, they're not super important. And then you have this so-called grid forming control layer that measures power or current injection into the grid, and it's basically adjusting the voltage reference, so both angle and magnitude that the converter is imposing at this point here. So when I'm talking about grid forming control, think of an object that looks at the power injection of the converter or the current injection, and then basically adjusts the voltage, angle, and magnitude reference to ensure kind of these self-synchronization properties of the machine that we have seen before, and to provide primary frequency control and so on, while imposing a stable AC voltage waveform onto the grid. So here is an overview of different methods that are prevalent in the literature here. So the oldest one is group control that originally came from microgrids, but it's something that you can definitely apply also on the transmission system. There's machine emulation, where you basically take the measurements of the injection into the grid and you run it through a simulation model of a machine to determine how would the voltage phasor of a machine respond. And then, you know, that's what you're applying to the grid. And then there are more methods that are inspired by self-synchronization of oscillators, standard virtual oscillator control, something that mimics a nonlinear oscillator, and those have self-synchronizing properties if you put them together. This is something that you will see quite a bit for single-phase inverters, but the original version of this, you couldn't give it power set points, so for transmission systems isn't particularly useful. And then something we came up with a few years back was this dispatchable virtual oscillator control, which you can give it power set points and voltage set points, and there are very strong theoretical guarantees, you know, as to what happens when you interconnect these things. So typically in the stability analysis of the group control and machine emulation, you have to drop these nonlinearities that we were talking about before and just look at the linearized system. For this dispatchable virtual oscillator control here, you can do a full nonlinear stability analysis. And so I could show you results for all of these things, but ultimately this dispatchable virtual oscillator control here has the strongest guarantee, and it's subsuming some of the other things, as we will see in a moment. So just to give you an idea as to what these stability conditions look like, I will show you the one for the dispatchable virtual oscillator control. Here are...
Could I ask a question, please?
Sure.
So I was curious. So I'm assuming when you have a network, there are certain generators that you assign this grid forming control to. Are those typically always synchronous generators, or could a renewable generator also, or is this grid forming control for renewable generators? I guess that's kind of what
I mean, it's for power converters, let me put it like this. But the problem is everything that I'm showing you here, you cannot apply it if it's a converter that is solely, you know, interfacing renewable generation. The problem being is you need to be able to control the power generation to a certain extent, right? So basically what you're seeing here right now, that is something you could apply to, let's say, a PV system that has a battery co-located there, and then a power converter, and then, you know, you would put this control on the power converter, and then it can contribute to stabilizing the grid.
I see. And just another follow-up. So with power converters, I'm assuming they're mostly interfaced with renewables, right? So when you're looking at the real-time operation of the grid, the share of renewables is changing over time, right? So would this control still be working even when the renewables aren't producing any?
No. No, exactly. So with the controls I'm showing you here, it will all fail miserably unless you put a battery on each and every one of these converters. Once we are past this, I will show you a control that addresses that problem.
Okay, thank you.
Sure, thanks. Okay, so just to give you a flavor for the type of guarantees that you can get, well, here's the control law, but let's not get into this too much. But basically the power set points you need to give this control, I mean, they need to obviously satisfy the AC power flow equations. And then you can see that, if the power transfer is small enough compared to what the network can handle, so you don't want any bottlenecks in your network. That's one of the key conditions for making this stable. Another interesting observation here, and this has to do with the circuit dynamics, you need to slow down this control enough so that it doesn't excite the circuit dynamics in the system. So that goes back to this, what I was mentioning before about timescale separation, that in synchronous machines, you're assuming, their response is so slow, it's not exciting any fast dynamics in the system. So, I just use the power flow equations to replace my network model. So with converter interface generation, you have to be a bit careful there. You need to actually enforce these timescale separation properties through the control. And what you see here is that basically for this control, you would have to tune it such that the voltage magnitude control is the slowest, then the droop-like response for synchronization is slower than what happens with the line currents if you write down the dynamic model for a transmission line. And then the time constants of these internal controls here that we looked at, they need to be the fastest. So you need to artificially induce these timescale separation properties again that are well known for machines to make sure that these things still work. Then one interesting point is that in this control law here, you will see this parameter kappa here that models the L/R ratio of the system. And then depending on how you select this, you can actually recover the standard virtual oscillator control. So this happens when you basically assume that it's a microgrid, that it's resistive, and you just drop the power set points to 0, then you get back the standard virtual oscillator control that I was mentioning before. You cannot give it power set points. So that in terms of equations look like this. Whereas if you connect it to a transmission system and you assume, that the resistance of the lines is 0, so that it's mostly inductive, and that, the voltage is near the nominal voltage because otherwise you're tripping protection, you're getting back droop control. So from that point of view, you can see that this dispatchable virtual oscillator control is generalizing many of these other controls that I've shown you. And while we have not done the analysis, similar considerations as to what you need to do for stability carry over to this one here. Let me skip this. So here's then a broader overview of all of these different things. And long story short, I will not bore you with the details, but if you want, you can look it up in this preprint here. So actually all of these controls that I was mentioning before, you can cut them up into controls that are designed for resistive grids, so microgrids or maybe distribution systems, and mostly inductive grids. And then you can basically, through different choices of parameters from dispatchable virtual oscillator control, you can recover all of these things here. And then later on, I will show that actually droop control and virtual synchronous machines and something else that we call dual port grid forming control, they're actually also the same if you just pick the parameters correctly. So there's a whole zoo of different grid forming methods in the literature, but ultimately in terms of their response, near the nominal operating point from the grid, they are very different. That's the message here. The core problem though with these things is, and this is, you were all alluding to these things earlier, is that, the stability certificates for this that I was showing, they're just for networks of 100% grid forming inverters. So this basically means, all these nice stability certificates, analytical stability certificates, they only work if you have only grid forming converters in your network. So no synchronous generators, no, PV that's doing maximum power point tracking. And all of these grid forming inverters are either backed by a battery or by a heavily curtailed renewable generation source that has a lot of flexibility. So, while this is nice from a theoretical point of view, reality, of course, has a mix of all of these devices. And as we heard before, fluctuations of different renewables, or they may not be renewable generation at all. So that's a problem. There's been some progress on modeling analytical stability certificates for heterogeneous systems and, studying the interactions of these grid forming controls with machine controls. But yeah, not a lot of progress on these things over the last years. And then there are things that are completely open and not well understood. And that's basically, first of all, the grid forming control subject to converter and power source constraints. that would be that, if you have a converter that is backed by photovoltaics, you cannot generate more than the maximum power point of the photovoltaics, even if you curtail it. It's completely not accounted for in the analysis of the controls that I've designed and analysis of the controls I've shown you before. Similarly, what's lacking is what I would call end-to-end stability certificates. So, your system has machines, the machine has a turbine governor system. The power converters interfacing the PV actually have, PV behind it or a wind turbine. And these things are not accounted for in the stability analysis, but we need to go kind of, end to end and not just cut it open at the converter and claim that, oh, there's enough generation behind it. We need to go from the generation sources to ideally the load. And then the final thing that is not well understood is like all of these things that I've shown you so far, I mean, they're all dependent on perfect knowledge of what's implemented in the converter, what does the network look like, what are the network parameters, which, as you can imagine, in large-scale power system, you won't really necessarily know these things. The system operator, may not know the exact parameters of a machine. A converter manufacturer will certainly not reveal, the exact details of the control that is inside of the converter. So those are all problems going forward. And so what I will talk about next is kind of something that addresses kind of the first 2 bullet points here. And then as an outlook, we can talk a bit about, how could data be used to overcome some of these issues when it comes to scalability and knowledge of the network parameters. Any other questions so far?
I didn't see a question from the chat box.
Okay.
Any questions directly here to Dominic? I think we are good. Thank you.
Okay.
Oh, there's a question. Sorry.
Yeah.
What is the
so what I'm using? Oh, yeah. Okay. Sorry, I'm a control systems person, by training. So for me, stability means Lyapunov stability, which basically means if you start the system near its nominal operating point, it stays near the nominal operating point and doesn't blow up. So frequency going unstable would mean frequency escaping to to 0 or to infinity. Whereas if you can keep it inside of the nominal operating region, that's something we would call stability, and then we would call it asymptotic stability, where after a perturbation it even goes back to the nominal operating point exactly. Okay.
Right. Okay.
Okay, good. So moving on. So as I mentioned before, one of the big challenges is now that we've seen the grid forming control that can basically stabilize the AC side of the converter and the network, and the AC grid following control that can form the DC voltage. So what I wanted to outline before moving on is that in today's system, you would typically need both of these things, right? So if you have an HVDC link, for instance, that is connecting an offshore wind farm to a main grid, what you would typically do is you will assume that the main grid is stable, then put a grid following control on the AC side of the onshore converter here. And that will in turn stabilize the voltage on the DC cable. And then offshore converter will assume that, the DC voltage is stable as an infinite bus. And then it will form a stable AC voltage waveform for the wind turbines to lock onto, which, if it's wind turbines with a back-to-back converter, they will again have one AC grid following converter that now locks onto this AC voltage waveform created by the HVDC converter, turn that into a stable DC voltage, and then again, from there, modulate this into a stable AC voltage that is doing the maximum power point tracking for the wind turbine. So you can see that a modern system where you implement all of these technologies, I mean, with these controls that I've shown you so far, you need a mix of them. And, there are no stability certificates for what happens when you mix these things. It's maybe not even clear if you think of an HVDC between different parts of the same country, that they would always operate in that configuration. So you could imagine a situation where this is one grid that is, very heavy on PV, and this is one grid that is very heavy on wind. And then depending on whether or not you just have a lot of sunshine right now and no wind, or vice versa, you may have to reconfigure these controls completely so that, once this system here can contribute to stabilizing this one, and once, you would have to do it the other way around. So even assigning these roles as, which converter should be grid following and which one should be grid forming is not a trivial problem. And we've looked at this for a few benchmark systems. So this is not published yet, but I mean, you should be able to submit it soon. And you can see that there are you can build benchmark systems that, include these things here and find a role as try to find a role assignment that is stable just for all possible load scenarios, not even changing the generation around too much, just changing the load flow. And we have a few examples where we haven't even been able to do this. So where, there's you can find one configuration of, of AC grid forming and grid following controls that maybe covers 80 or 90% of the load flow scenarios, but you cannot go to 100 without changing these assignments around. And that's of course also a big concern because, changing these control assignments in real time while the system operates can be quite challenging. So let me skip over this. So let me show you what the solution for this may be. And, those are some early results that we just published in Transactions on Control of Network Systems. And also have a few application papers on the way. So on the very left here, you see the grid following control. And the problem here was basically that we say, oh, the grid is stable and we just inject power into the grid and, the grid will take it and nothing bad will happen in the grid. So we use that property to stabilize the source behind the converter, be it in HVDC, wind turbine, PV. The grid forming control, on the other hand, was saying, oh, let's ignore the power source completely. Let's assume that can keep up, and we contribute to stabilizing the grid. But ultimately, the way it should work is that whichever of these two sides has flexibility should support the other one. Because ultimately, the main problem with the grid forming control is it's treating the power converter as a power source, but it's not really. I mean, it's just converting power from something that generates it to the grid. It's not generating any power. And the power balance kind of between these two sides is actually crucial to operating such a system. So if you have the AC grid forming control, you're saying, oh, the DC voltage is stiff, let me stabilize the AC side. If you have the grid following control, I'm saying, oh, the grid is very stiff, has a stiff frequency, let me stabilize the DC side. But what you actually would like to see is that this is bidirectional, right? So if I'm running the power source here at the maximum power point, there's no more flexibility to do control here, then it should be stabilized from the grid. Whereas if I curtail this and have flexibility, then within that flexibility, I should be able to contribute to stabilizing the grid. And so here's a control that gets the job done and basically links back to how a machine works. So remember, we were discussing the machine here and we were saying, okay, the frequency here is the indicator of power imbalance, right? So if the power generated by the turbine, let me call it PM, the power flowing into the system and drawn by the load is called PAC. And the frequency is the integral of that power imbalance multiplied by the inverse of the inertia coefficient. And the interesting part here is now we had this question earlier about what happens with the grid forming control if the renewable source behind the converter that's not generating anything. Well, then the grid forming control fails. But in a machine that still works, right? If you have a synchronous condenser, that's a synchronous machine without the turbine, and that still provides inertia support and voltage regulation, and at least partially gives you some of these grid forming services. So we can actually do the same with the power converter. So here in the power converter, the energy stored in the converter itself is the analog to the frequency. So in a two-level converter, that would be the voltage of the DC link capacitor. So any power that gets injected into the grid comes out of this DC link capacitor, and then the source is putting more power in. So long story short, the integral of the power mismatch here is the DC voltage. And based on this, you can basically have the analog to a machine where you say, oh, if the DC voltage goes down, then we draw down the frequency with a certain gain that would entice the DC source to give an increased response. And we will see in a moment that, for instance, PV and wind turbines exactly do this. And this type of control, basically now if the source behind your converter has no flexibility anymore, so it's at the maximum power point or there is no sun shining, you are still getting services like frequency oscillation damping and volt-var control. You're losing the primary frequency control, but you're not losing all of the services. Whereas the grid forming controls that I've shown you before, they just go completely unstable in that situation. So here's the controller that we have, where you basically adjust the frequency of the voltage waveform that the converter is putting onto the grid, depending on the mismatch in the power injection and the mismatch in the DC voltage from its set point. And we're calling this dual port grid forming control because it's basically aiming to stabilize the voltage on both sides, both on the DC and on the AC side. There are many variations of this. So you see this is basically droop plus a DC voltage control term, if you're familiar with these types of controls. You can change this to, and wonder like, why should I have this AC power set point here if that's not in line with what the DC source is proposing? So you could also put the difference between DC and AC power here. Another variation is you could try to account for losses, which you don't really know, but you could estimate them. Or actually, if you look at this here, you see that the integral of the mismatch between the power being generated on the DC side and what I'm injecting on the AC side is actually the DC voltage. So I could also replace this whole thing here with the derivative of the DC voltage. So these all have slightly different properties, and I don't really want to go into the details for each and every one of them. You can look it up into in these papers here. But the key point is now for all of these controls that I've shown you, I can give you stability conditions that basically account for the generation behind the converter. They account for the presence of synchronous generators, so machines with the turbine governor system, and synchronous condensers, so machines that don't have the turbine governor system in the same system, and can certify at least small signal stability for these things. So we're back in the linear regime, but the non-linearities have been removed by linearization. And so why does it work? So here's as an example, just PV. And remember, these controls, they roughly tie frequency to DC voltage. So what you see here is the power generation by a PV panel for different levels of irradiation. You see the maximum power point here are the circles. And if you operate at a curtailed operating point here at a higher DC voltage, say we pick this one here, and now you have a load step in the system where then the DC voltage drops, and that increases the power generation and basically immediately gives you a primary frequency control response. Whereas when you're up here, a change in DC voltage due to load increase would basically mean very little change in the power injection. And then you would mostly kind of draw power from the AC side to stabilize the DC side if needed. And that control will just autonomously do this, right? There's no mode switching between grid forming and grid following things. It's just one of these stupidly simple controls that I've shown you here before. And it's basically automatically doing this. So long story short, if you use that control and you have a renewable source at the maximum power point, it will just be a slightly more resilient version of the maximum power point control that does away with this phase lock loop and all the fragility associated with this. Whereas if you operate below the maximum power point, you get inertia support, primary frequency control, and so on. And it's similar for a wind turbine, but in the interest of time, let me move on here. The even stronger point from our point of view is now because there's no longer a mix of different controls, and these controls can kind of autonomously transition between these operating modes. We have much stronger stability guarantees. So here's kind of the model that we use for stability analysis. So we think of the system as kind of living on a graph where we have AC nodes and lines. So this is what you see in red here. We have DC nodes and edges that's marked in black, and then we have converter nodes. So those would be the power converters that translate between DC and AC. So you can think of This is an HVDC link, this could be an offshore wind farm with, a bunch of power converters. And then these red nodes here could be machines, for instance, and this would be a machine node. This would be a machine node. Those could be PVs on a DC network. So it's extremely general. And then we have these very crude reduced order models that model basically the power flow in the AC network as a function of angle differences, and the power flow in the DC networks as function of DC voltage differences. And then you can basically use all of these reduced order models that I've shown you before. So here's the one for a synchronous machine. Here's the one for a turbine. For a DC AC converter, it's fairly similar. Here, the charge dynamics of the DC capacitor, AC power flowing out, power flowing into a DC network, and the power that's being generated by whatever is behind the converter. And then the DC power source, you can again model it as something linearized that's responding to DC voltage deviations. So basically you see over here the turbine governor system of the machines, or this can also be used as a linearized dynamic for a wind turbine. You see this coefficient Kg here. This is basically modeling the sensitivity of your generation source with respect to a change in frequency. And similarly, you can write this down for a DC power source. And again, this Kg here now is the sensitivity with respect to a change in DC voltage. So you can see for PV, if you're up here, then this Kg is equal to 0. Whereas if you're here, it's a positive number. And you basically inject power relative to DC voltage perturbations or fluctuations. So all of these things are basically interconnected through these graph models here. And through this, can model a very wide range of devices. So a wind turbine with, back-to-back converter would be two of these converters connected through a DC network. And then on one side, you can have like a machine or, an HVDC, that's again another DC network. And then on the wind turbine side, you would have a machine that's, the permanent magnet synchronous generator in the wind turbine. And the aerodynamics would go into this linearized power source equation here. So basically through this framework, you can, from these very simple reduced order kind of constituent models of every power conversion or generation device and this graph structure, you can just plug everything together and build synchronous machines, synchronous condensers, PV, HVDC, flywheel energy storage systems. So it's extremely flexible, but the individual models are quite crude. Let me put it like this.
Could I ask a question?
Yeah, sure.
Could you speak a little to how you choose the granularity of these models? For instance, when you're modeling synchronous machine, using swing equations versus using a more higher order model. So how do you go about choosing that for when you have for this analysis, when you're trying to do an end-to-end stability analysis?
So here we really just went with the simplest models that could be justified, just to simplify the analysis a bit. That's the main approach here. So you could imagine that if you make these more complicated, then the analysis becomes more complicated. So for instance, certainly for the DC-AC converter, we know how we would be able to extend this to also include the inner loops. For the synchronous machine, it's very difficult. So if you were to include the stator dynamics, for instance, or like a PSS, then probably everything that I will show you next will fall apart. I mean, in practice, it still works. I will show you simulation examples. But really the key to getting to the result I will show you next was really just using the simplest model available.
I see. Okay. And generally speaking, how important do you think those higher order dynamics are, just from experience?
Yeah, so there are two answers I can give to this. So we have extensively analyzed this for standard grid forming controls. And there it's actually quite important. So the answer to this for standard grid forming controls is that you need to put bounds on the control gains of the DC-AC converter to make sure that stability of this reduced order model here carries over to stability for the full model. So based on that experience, what I would say is, if you make this gain MP here or this gain K theta here too large, then all of this breaks down. So typically what this all boils down to is, these reduced order models, they're valid on certain timescales and they're valid in certain neighborhoods of the nominal operating point. right? And that's kind of the part where it becomes a bit tricky. So for very large disturbances, this is not going to be valid. For very high converter control gains, where you get like a super fast response of the converter, this is not going to be valid. We're certainly thinking about, pushing it a bit further into that direction. But, for now, it's these simple models. I saw there's another question in the chat of intermittent nature of the renewables. Yeah, this is not accounted for here. So the assumption here is at the moment that it's a snapshot of the system at a certain point in time, for a few seconds, and that, there's going to be very little variability on that time scale. It's actually one of the open problems. I had a whole slide on this at the very end, but, let me talk a bit about it now. But this will boil down to is that at any point in time, if you want to translate kind of this deterministic result here into a stochastic setting, is that at any point in time, there need to be enough power sources that have flexibility and respond to power imbalances as captured, by frequency or DC voltage imbalances. And then this is going to work. Now the question becomes, how do you rigorously show that from a theoretical point of view, and from a practical point of view? How do you make sure that this is correct, right? So let's say I'm a system operator, I have my day ahead forecast, and then for tomorrow, I want to be sure that there is going to be enough devices that actually contribute to stabilizing the grid so that all of this works. Then, what does the forecast have to look like? What margin do I need to put on these things? So those are all things I don't have an answer to, but I think, at least with a framework like this that now allows you to have all of these heterogeneous technologies in a coherent model, that's something I would see as the next step, kind of tackling all of these questions. Okay, so let me show you what we can do in the deterministic setting. And let me switch over the details in the notation here. So what we need to show stability in the deterministic setting is that, okay, we need at least one node that has, this positive control gain kg, so that it's responding to power imbalances in the system. We have this somewhat technical condition here, which says that one of the gains of these of this dual port grid forming control needs to be the same for all converters that are on the same DC network. So it could be different, let's say, for this converter and this one here, but for those two, some of the gains have to be identical. And that has to do with kind of a network coherency thing. You could imagine having a second HVDC from this node to this one here. And then if these gains are not the same on both ends of these two HVDCs, a certain frequency deviation in this network here would map into different frequency deviations at this node and at this node here. And then you're in trouble, right? Because then it can never synchronize. So that's encoded by this one here. So suffice to say, there are some gains where if converters are on the same DC network, they have to get the same gain, and that restricts, what you can do a bit. And then from there on out, the main question is the system, the AC system in question, so all of these red parts here, those are what we need to look at. Is it machine dominated? So does it have more machines than converters, or is it converter dominated and has more power converters than machines? And for both of these cases, we can basically cut up the AC nodes into different sets. In a machine-dominated system, that would be machines and power converters that are backed by a source that has flexibility, and then machines that don't have any source or don't have any flexibility behind it. So like synchronous condenser, flywheel, wind turbine at the maximum power point. In a converter-dominated system, you can just cut it up into converters and machines. And the crucial part is now you only care about connections between devices in these two groups. And you can check that for each AC network in isolation. And there is a somewhat technical definition here. But basically what this condition here is saying is that, if you have devices in these two groups, so loosely speaking, devices that contribute to stabilizing the system and devices that don't, you need enough connections, you need enough connectivity between them. So this is what this is saying. We have a bunch of extensions to this, like, an n-x stability condition where you say, look, can I still certify stability if I lose like one line, two lines, one machine, two machines, and so on? Also steady state analysis as to, how do these things affect the steady state frequency after load perturbation. I'll not go into the details of this here. And maybe to give a high level interpretation of what's going on here is that if you have a machine dominated AC system, you need enough sources that respond to imbalances, and you need enough connections from synchronous condensers or flywheels and so on to sources that respond to imbalances. Whereas if you're in a converter dominated systems, it's basically the machines that you need to worry about, and you need kind of a tight enough connectivity between machines and converters and the sources that respond to the imbalances. There, for DC networks, there, as I said, the restrictions on the control gains, but no conditions on the topology. So in that sense, I mean, these conditions here are fairly mild. I mean, they're basically just encoding what you would have expected. In a very weakly connected systems, like the Australian system I've shown you before, you will kind of locally in every neighborhood, you will need some resource that responds to imbalances. Whereas if it's a very strongly coupled system, I mean, these resources can be anywhere in the system because, they will have connections, strong connections from there to any part of the system, and then it's also going to be fine. So maybe to give an example as to what this means, here's a system that, this is a flywheel, so, machine, back-to-back converter, then you have wind turbines here connected through an HVDC, so it's a wind turbine with a back-to-back converter, and then here, the HVDC network, and then here an AC network that has a machine and a PV attached to it. And to verify these stability conditions, you can cut this up, so you don't need to look at DC networks as long as all of this is connected. So you can look at every AC network in isolation. Then for every AC network, we can cut it up into these different groups that I was mentioning. So here you see this is converter dominated, so this is where the power converters end up in this group C here. Same here. And now for each of those, we can check this condition that I was mentioning as to whether or not there is a connection. So we see here, there's a connection between the two groups. There's a direct connection here between the two groups, same here. So we are done, and that type of system would be stable. Now, the main issue is, as you see, I'm using partial knowledge of the network here. I'm using kind of partial knowledge of, these sensitivities, these parameters kg of these renewable resources here to even arrive at this partitioning. So all of these things, are something that once the system becomes stochastic, all of this will be time varying and changing, and I can no longer see this as a static problem, and that would be quite interesting to tackle. Okay, so this is just a theorem that says, if all of these things are true, then this is stable. What I would like to highlight is it seems to cover most practically relevant cases. We went kind of through all these things like, wind turbines with back-to-back topology, flywheels, and so on. We can cover most of these, or actually all of them that we've looked at. Another thing is you will notice here that the topology of the system factors into this quite heavily. And for standard grid forming control, interestingly, it doesn't, right? So when I was talking about the network of only grid forming converters with, backed by a battery or whatever, the network topology didn't play a role. So for this more generalized setting here, where you can have machines, where you can have renewables and so on, the topology all of a sudden starts to matter. And it's not only the stability condition that I showed you here, we actually have counterexamples. So they're very simple counterexamples of one synchronous machine that has a turbine governor system connected to two synchronous machines that don't, so synchronous condensers. And then already they're always, for any parameterization of the machine, so for any damping and inertia coefficient, there exist network parameters so that it goes unstable. So you can no longer, once you mix all of these technologies, topology starts to matter, and you can no longer find stability conditions that work kind of for all possible interconnections. Okay, so that's the picture I've shown before. So, see here we have this dual pod grid forming control, and then if there's one coefficient, if I drop it to 0, I get the group control. If I put another coefficient to 0, I get kind of these machine emulation controls. That's again one of the was one of the missing pieces, actually, where you can see that, you know, different parameterizations of this dual pod grid forming control can either give you droop control or machine emulation controls. Okay, so those were the take-home messages here, that, you know, this universal control now allows you to mix all of these technologies, supports all of these different functions, and we can kind of give relatively good stability conditions for this. But of course, you know, open question is what happens with more detailed network and device models, as we discussed. What happens, you know, when a converter manufacturer, I mean, you cannot, as an operator, you cannot force a converter manufacturer to actually implement this particular control. They may implement some variant of this, right? So what happens then? What happens if the system topology or the flexibility of the devices is time varying? This will change these sets CI and DI that I showed you. And then, you know, every time you would have to go through these stability conditions, and you don't even know what these changes are going to be, you know, a day out. So these are all open at this point. And as we'll get to in a moment, I think these would be very interesting points, you know, to take more of a data-driven or data-enabled perspective. So to show a few examples, here's a power system where we have a synchronous machine with a turbine governor system. So this is an IEEE 9-bus system now with here battery storage system, here PV system, an HVDC connecting this to yet another system. Sure, yeah. I mean, I think the video of this is also going to be published, right?
Yes, we are.
Okay. And yeah, I can also make the slides available. So yeah, so here's kind of just a system that is mixing all of these different things. And, you know, with the standard approach, you would have to mix at least 4 standard controls. So here we're running the same control on all of them. You can go through this system, and this is in this, so I put the archive reference here, but in the meanwhile, this has been accepted and published in TCNS. Go through this and check these, you know, topology-based stability conditions, and it works out for that system here. And basically here, what you can also see in that system is the grid support is transparently passed through the HVDC. So, you know, if there's a load step here, you also get parts of the primary frequency control response from the system here. And just another thing to highlight, this PV system here is operating at the maximum power point. So you see here, there's a load step here at this point in time. And you basically see this PV here is not changing its power injection, it's just staying flat. And I didn't plot, you know, frequencies and reactive, voltage and reactive power here, but you can still see it's still providing oscillation damping and volt-var support. So that just goes to highlight this point that I was mentioning before. It's now wherever you dispatch the power source and whether or not it has flexibility or not, that decides about the level of grid support that you're getting. So that's the same system where now, instead of this synchronous condenser that we had before, we plugged in a wind turbine with back-to-back converters, very similar result. So I will probably not spend time on this here right now. And then we also have a paper here. This, again, sorry, this is still the archive link. This has been accepted for transactions on power delivery, where we again kind of put these dual pod grid forming controls on all of the HVDC converters here. And again, we kind of get everything to work with a single universal control. So, and that's the final one. That's something that just got accepted for IRAP, where we made a more detailed, where we investigated this on a far more detailed wind turbine model than what I've shown you before. And again, you can see here, the red dashed line is a grid following maximum power point tracking wind turbine control for this system here. And then we have 2 things as comparison points here. The blue, solid blue line is the universal grid forming controller that I was just discussing, but the wind turbine operated at the maximum power point. And then you see here, there's a load step in the system here. And you can see that you get so this is the active power injection. You can see that there is a bit of power being drawn kind of from the rotating mass of the wind turbine. So you get like a bit of an inertia response here, but, you know, not a lot. Whereas, you know, the grid following maximum power point tracking gives you nothing. And then if you curtail the operating point of the wind turbine, and operate at a higher rotor speed, you're basically reducing the power production at the original operating point, but then you see after the load step, you get this massive boost of energy that gets released from the rotating mass by decelerating it, and then you have also a primary frequency response, so that after the contingency, you get more power injection. And then you can also see that the frequency response of the system, so it would be the frequency taken over here on the machine bus, is significantly better once you curtail the wind turbine, and it contributes to frequency regulation, versus the other two controls that basically just do maximum power point tracking and give you this massive frequency nadir here. You can basically see the shape for the maximum power point tracking ones looks like what I predicted way back at the beginning, using the center of inertia frequency model, whereas the one that is actually providing a frequency response decreases the frequency nadir quite dramatically. So that's just a few examples. And then let me get to this point that I was promising all along, like how do these things tie into data and data-driven analysis. So the crucial assumptions I've made so far was that every converter is using the same control. We do have partial knowledge of the network for our stability certificates. Actually, when we want to optimize, and this is for stability, right? And stability doesn't equal performance. And then when I was talking about performance, where in the network do I place these virtual inertia devices, for instance, to get a nice frequency response? That actually required full knowledge of the system to do this. And the results that we have so far, they give you a bit of robustness because they allow for kind of small changes in the network and devices, but this is more like, an N-1, N-2 flavor, where you can lose a line or a device here or there. But, in reality, there would be rapid changes between these things potentially, right? Let's say one day is very cloudy, the next is very sunny, that can change the flexibility between these things completely. Then, as I was mentioning, in reality, we do have proprietary converter hardware and control implementations by different manufacturers, and we actually do not have full knowledge of the system, and especially there are lots of legacy devices for which we maybe even don't have a dynamic model. So lots of things we don't know that, in the analysis, I assumed I know it perfectly. So those are kind of the main points. And to maybe go through them one by one a bit. For instance, right now, if you want to do kind of a pre-qualification test of a synchronous generator, it's relatively straightforward. If you look at grid codes, for instance, in Europe, they will show you pictures like this. So they will basically say, oh, I'm subjecting the device to be connected, and I'm showing it a drop in frequency. So you see this frequency ramp here from 0 to 10 seconds. It drops from 50 to 49.8 hertz. And then the power injection of the machine has to stay within these minimum and maximum thresholds within these dotted lines here, right? So you see it's supposed to go up here, then it can have an undershoot or an overshoot, but that's limited by these lines here. And then ultimately in steady state, it has to end up within 5% of the droop response that was promised. And these types of specifications, they work because the synchronous generator dynamics are mostly governed by physics, and the reduced order models, they're all these swing equation models that I showed you before. It doesn't matter if you bought this from Siemens or from ABB. And on top of this, the free parameters in these reduced order models, they are all proportional to the machine rating. And none of this will work like this with the power converter anymore, because on the power converter, the dynamic response is given by software, right? So you can do a lot more things that are not necessarily proportional to the rating, that are not necessarily the same in different operating regimes. So if you think back to these emission scandals in the automotive industry, you could do something like this here, right? You could detect this frequency ramp, and then you could basically implement the response that is needed by the grid code. But then, if there's a different frequency ramp, the response could be completely different. So it's because everything is software, you have that flexibility. And now the problem is, how would you test these things to make sure that they're working under interconnection? How would you cover all of these corner cases without, falling into this trap of showing one signal to the converter and just from this concluding that everything is fine? So the way I would envision these things to work is that, the converter interface generation is basically a highly complicated black box. You have no visibility into the internals or controls, but you can try to learn what's in the box from the terminal behavior, right? You can basically take the converter as a device under test. You can hook it up to a network or to an AC source. You can show it perturbations, and you can try to identify using system identification tools or learning tools the internal dynamics from what you're seeing at the terminals of the device. And then you can compare that to a known good behavior, like the control that I've shown you before. Or you could try to say, if I put certain bounds on this behavior that I'm identifying or learning, then hopefully it can certify stability. So I see this as kind of as a pathway to data-enabled stability certificates, where you can turn basically the core properties of the converter controls that I've shown you before into bounds on the dynamics that each device should be exhibiting. And I don't have the results ready to show them yet here, but I've been starting to work on this with a student, and I mean the results look quite promising in the sense that there are kind of clear bounds emerging if you look at various different grid forming controls and these universal controls that I've just shown you. You can basically see that they're all kind of falling within the same bounded behavior of each other. So this goes back to this graphic that I was showing as like, if you pick certain parameters the right way, then these controls become identical, right? So from this, you can basically specify something that is kind of a known good behavior. Now the question is, how far can these individual things deviate from this so that when you put it together, it's still stable? So that would be at the device level, and that would basically be like almost an adversarial setting, where you try to find a test signal that excites something in the device that tells you what's inside of it, or at least if it lives within your bounds. Second problem, and this is okay, let me maybe answer the question in the chat. So would be a worst case robust stability analysis. Yeah, I'm not sure yet. That's something we've been trying to wrap our heads around. Ideally, I would prefer something that has more of an average notion, in the sense that if on average enough of these devices are close, then it should work. But I mean, who knows? It may very well be that an individual one that is too far away can destroy stability for the entire system, and then it would have to be worst case robust stability guarantee. So it's a question that, it's a very good question. It's one that we have been wondering about, but I don't have a good answer yet. Then the bigger problem is that I was mentioning before. So now let's assume, the devices do what they should. What we've seen in these stability conditions that I've shown is that, the local flexibility and reserves of the individual source, I mean, that matters a lot. That, decides which category your device ends up in. And then we need, or rather which of these two groups, right? And then we needed kind of enough lines or connections between these groups of devices. And I mean, all of this may be subject to change dynamically because the flexibility and reserves change, it changes the composition of these different groups. And then it changes which connections you would like to look at. And now imagine that you're a system operator. There are millions of these things, and you somehow need to make sure that, tomorrow all of this works. So one approach would be to say, we use the day ahead forecast and some statistical analysis to guarantee that, under the forecast error, the day ahead forecast from today guarantees that I have enough of these devices with flexibility tomorrow, and they're, spread out enough throughout the system. So we have done a very naive version of this a few years back, where we didn't account for the topology because, back then we didn't know that the topology factors into it. So that analysis was basically, you can find it in this paper here. This was just a worst case analysis. So the worst case prediction error of the day ahead forecast, and then the entire system was clubbed together into the center of inertia model that I showed at the very beginning. And then of course, this is relatively straightforward. And for that setup, you can find fairly good bounds. The question now becomes, if this becomes a setup where the devices are spread out in a weakly coupled system. So now all of a sudden you need to have enough of these devices with flexibility in every neighborhood of the system, right? And not just in one place. Then this becomes a lot more complicated. And especially, how do you identify then these critical connections that I was talking about? In a very closely meshed network, it's probably not an issue, but in one that has like a very kind of, very loose interconnection and very long lines, that may be a problem. The final thing is that, as we were alluding to earlier, I mean, for the analysis, I used extremely crude models, like a swing equation model for a synchronous generator. It doesn't even account for, for the PSS. It certainly doesn't account for protection. So one question would be, are there similar abstract models for other legacy devices that we didn't account for? And can these things somehow be learned from data? Because, for the synchronous generators, the swing equation model is not critical in the sense that, we know the parameters are somehow proportional to the rating, right? But for other legacy devices, that may not be the case. And then that's also a question of, like, how do you get this in there? And then ultimately the question is, how would you bundle all of this up to get some stochastic stability certificates that, as I was mentioning before, ideally would have this flavor of, I have enough of these devices on average, both kind of, average over time and average over space, and then it should be fine. No, I would say physical models, like physical reduced order models with physical reduced order models with learned parameters. Just because I have no idea how to do this type of analysis within completely unstructured models. There are some results that would allow, basically, as long as you know the network topology, you could go with the completely unstructured model of, say, the transfer function between the power injection into the grid and the voltage angle that the converter is putting on the network, but we have not really explored those. Okay, and then finally, so you see I'm zooming out at bigger and bigger problems. There's this tuning and placement problem that I was mentioning. So, stability is one issue, right? But then you also want good performance. And that's the same question in the sense that what I've shown you was that, if the system is very strongly coupled, it doesn't matter where you put these devices that have the flexibility, or that do the inertia emulation or the fast frequency response. If the network is very weakly coupled, the only option right now is that you run an optimization kind of, with the full knowledge of the system, but there should be something in between, right? Can we maybe learn a reduced order model that, is maybe modeling these areas as not the entire system as one swing equation, but maybe every area is one swing equation. And then if I have a very weak area, that's what I would like to reinforce, right? So there's all these things in between where, analytically speaking, it's a bit hopeless to derive these models and these bounds if the systems become super large, but maybe there's a data-driven or learning perspective on these things. And that basically goes back to that fact of, if you have these systems that use a mix of all of these technologies, as I was mentioning, the placement of some of these converters really matters, right? So you could think of using this universal control or standard grid forming controls backed by a battery. And the question then becomes, where do we put these things? Question in the chat about how do we characterize network as strong versus weakly coupled. So it depends on two things. One would be the admittance of the lines, right? So you can imagine that if you have a very long line that has a lot of impedance, and that will basically just decouple the ends of the lines, in the sense that for the same angle difference, phase angle difference over the line, there's going to be only very small power change in the power flow. So that would be an example for decoupling. The other one would be, sorry, let me rephrase this. You can either have, a lot of lines, but they could be relatively high impedance, and then it doesn't matter. Or you can have one line, with a very low impedance, very high admittance, and then would also be strongly coupled. So I think it's both in terms of how many lines do you have between different parts of the system, and how big is their impedance. At least that's the way we're using it here.